All right, let's get into some more practical stuff with physics. The machine, because it sends out a pulse and then listens, determines how far away an object is based on how long it took for that pulse or echo to come back. So if this on top is an ultrasound transducer, and here's an object in the body, and over here is the ultrasound screen. When the ultrasound beam is turned on and starts to pulse sound, and this repeats over and over again, refreshes, which is why the images move dynamically, but we'll show you just one pulse and listen cycle. There goes the beam, it bounces off the structure, it comes back, and it took a really short time. So the machine represents that image close to the top of the screen. Also, from a practical standpoint, nomenclature-wise, for absolutely 99.9% of the imaging you're doing, with one or two rare exceptions, you're going to have the probe and the screen oriented in a way where the top of the screen corresponds to the patient's skin, and this is deep into the patient. That could be anterior, it could be posterior, it could be lateral, coronal. It just depends on which way the probe's positioned on the patient's body. But regardless, the top of the screen is going to correspond to the patient's skin. Now, as a result, the top half of the screen is referred to as the near field, and the bottom half of the screen is referred to as the far field. So just some nomenclature to be aware of, because you'll hear these terms pop up. So pulse comes out, strikes an object, returns back quickly. The machine represents that object on the screen in the near field because it didn't take a long time for that wave to come back, and it assumes it must be close. Now contrast that if we move the object down and pulse. Now the pulse comes out, and we're waiting, and it comes back. And that long time of flight tells the machine that that object must be further away. And as a result, in this case, it gets displayed in the far field. Okay, so we know that time equals distance. We know that structures deep on the screen must be further away from the ultrasound probe, and that makes sense. Now, the only other real basic thing we need to understand about physics is what happens when that pulse strikes an object. And there's really three broad categories of what can happen. In this case, the pulse strikes an object. That object reflects almost all of the ultrasound waves back to the transducer. And as a result, the amplitude, or the bigness, of the returning waves is high. And because of that, there's a lot of returning echoes, and it is therefore a hyperechoic, lots of echoes, image that gets displayed. Hyperechoic is bright, or echogenic. Those terms tend to be used interchangeably. And we'll see structures in the body that are echogenic have similar characteristics. So in the body, the things that are most commonly echogenic are things with high calcium scores. So here we have the scapula, and down here the proximal humerus in a patient with a glenohumeral dislocation. And over here we have a ureterovesicular junction ureteral calculus. So we're looking at bone being echogenic and stones being echogenic. The prior slide had gallstones, also echogenic. Tendons can have high echogenicity. Other structures will as well, but for the most part, if you remember that bones and stones are typically bright and shadow deep to them, which we'll cover in the artifact section, you'll be in pretty good shape. On the other end of the spectrum, what if the ultrasound wave comes out and passes directly through an object and doesn't get reflected at all back to the ultrasound transducer? Well, that's going to be devoid of echoes, or anechoic, lacking echoes, and that's going to be black. So on this image, we're seeing, first of all, here those gallstones that we pointed out on the echogenic spectrum, and then all of this black, which is bile, which is anechoic, and fluid on ultrasound is black. So anything that appears anechoic on ultrasound, truly anechoic, not dark, but black, is going to either be fluid or shadowing. And shadowing is usually pretty easy to identify, and we'll talk about that, like I mentioned, in the artifact section. So looking here, this is anechoic. We have on the left side of the screen a large abdominal aortic aneurysm that's about 5 by 5. It's got a bunch of mural thrombus here, which is included appropriately in the measurements because that's all part of the aorta. But the lumen of the aorta over here is anechoic. It's containing black blood. Over here we have an ocular ultrasound with evidence of a retinal detachment, but the bulk of the intraocular contents are black because we're looking at posterior chamber and we're looking at vitreous humor. So anechoic structures are black, whether that's urine, it's blood, it's bile, it's ocular contents. Anything that is fluid-filled will be black or anechoic on ultrasound. And lastly, the much more broad category is structures that reflect some of the ultrasound waves, but allow some of them to transmit. And in those cases, you'll see some degree of gray. And how do you call a gray? What do you call a gray structure on ultrasound? Well, it really depends about the surrounding structures. If it's brighter than the surrounding structures, it'll be hyperechoic with respect to them. If it's darker than the surrounding structures, it'll be hypoechoic with respect to those structures. It may be isoechoic, similarly echogenic. So that really is more of a relative term when you see some reflection and some transmission of ultrasound waves. What's